colloids, and colloids are a cool part of soft matter as well. And I will show you that there are a few things we can do that are interesting and maybe useful as well. For instance, for diagnostics, and also a little bit for photonics. So I will mainly speak about colloidal assembly, and just we can wonder why we should care about assembling objects in general. First, there is kind of, I think, of general taste for things that are ordered. Even if at home we can like to have some mess, in general, when we go somewhere, we like when things are organized. And it's quite important for when you have, when you think about integrating functionality, usually you have to organize things properly, right? So it's not enough to have very beautiful crystals of colloids or of whatever, of nanoparticle. You need to be able to integrate it in functional devices. And for that, you really need to be able to control the assembly. It's very important as well. And third, which is, I think, quite important, is that when you do self-assembly in general, whatever it is, colloids or something else, is that it's, in terms of properties, it's not just additional. You have additional effects, okay? If you take many colloids, you will have many times more the properties of one guy. If you are all up here and you scream, if you scream together, it will be very loud. But you have also collective properties and coupling properties, meaning that you will have some new properties that emerge because you have something that is self-assembled. And this is something interesting, is that it's not only about multiplication, it's also about generating new functions. And you have many collective properties, magnetic properties, electronic properties, photonic properties. And you have this, I think, just visible example of structural colors is that you can take non-colored objects, non-pigments, and if they are properly assembled, then you can have colors. You can have these beautiful structural colors, such as on a morpho butterfly, but you can see on many insects, birds, and so on and so forth. So you can generate new properties because of the organization of your individual bricks. So you see, it's important to have functional device. Something is quite important is that when you do assembly, it has to be done properly. So you see here, I have the proper elements, but if I have a mistake, then I lose the function, right? So this is quite a challenge in when we'll do assembly, is to try to do the assembly in a much flawless possible manner, meaning you need to deal with defects and you need to beat the defects. So I see two types of assembly. It's my definition. I don't say this is the definition, it's my definition. So I see really two different ways. One is directed assembly. So I take some materials that don't have any information. It can be some wool strands. And then I have a super smart user. And this user will transform this non-informed material into a functional assembly, right? So this type of assembly has interest, and one of its interests is that it's arbitrary in terms of bricks and shape, as long as I have a proper method. For instance, I can choose to replace this by a nylon thread, by fishing line, by metallic cable, and by almost the same principle, I can get the same assembly. This is something great. You don't rely on the information so much that is in the material, but you rely on your methodology itself. So that's quite cool, but it's supervised. It means that you need to have something or somebody who is doing this operation. So you need to supervise the process. And this, of course, makes it prone to mistakes. I gave the example of the chair before. Obviously, it's not the chair that makes the mistake, it's the user who didn't assemble properly. So you can get functional assembly, you have a lot of advantage in directed assembly, but it's user-driven, it's user-dependent. If I take this example, if some of you in this room like knitting, it's maybe a bit improbable in Kerala because the need of to wool is a little bit limited. But imagine you have 3 people, even if they follow the same process, they will not have the same skills, and some will be very beautiful, and at the end, some will be not so beautiful. So it's user dependent. So the other way you can think about self-assembly is self-assembly. And my definition in self-assembly is that the information is in the brick itself. And it's the interaction between these bricks through their informations that will lead to the final assembly. So what is very nice in this process is now you have something that is user-free, that is autonomous. So you don't have any more the supervision aspect. You have your bricks and the self-assembly. There is also a possible mistake in this process. And the main things you have to fight with are kinetic traps. So this is my thermodynamic equilibrium, because this is where all my information has been processed in the best way. So my energy minimum is there on the ground, and I'm starting somewhere very high in energy. And little by little, all this information will be combined and they will reach the minimum of energy. But kinetic traps means that maybe at some point, system will assemble and will be in some local minimal, and it will be trapped. Okay, and it's like when you take something, imagine you are starting to self-assemble and suddenly you freeze everything, like with temperature, you stop everything, and then you are a kinetic trap and you have mistakes. That makes that self-assembly, this is the main challenge in self-assembly, is the kinetic traps. The thing that you put all your bricks, they have information, but at some point they will be frozen somewhere because they will be trapped in some local minimum. And also, another challenge with the self-assembly is to get high reconfigurability on dynamics, because if you program, if you have information in your bricks, how they will change their interaction to be reconfigurable, because the information is inside the bricks, right? And that's also quite interesting intellectually to think how we can have self-assembly, so information, so that the system can self-assemble without mistake, so it's capable to do that, but at the same time it's also capable to transform. This is now something that is quite challenging. But so today I will show, the things I will show will always be between directed and self-assembly itself, but we try to go to our self-assembly and try to make quite interesting behavior. So the last things I would like to say as a general introduction about self-assembly is that I think it's quite interesting to compare, because this was a bit how this course was constructed, but to compare synthetic and natural self-assembly. In synthetic self-assembly, if you take a micelle, for example, it's a typical self-assembled system, you work at equilibrium. So you put your bricks, they assemble, and you are at equilibrium. And you get well-defined and well-controlled structure. Your property will be defined. If I take micelles, it will be defined by the packing parameters. You just take the book of Israel-Ashvili, you open at the page, I don't know, and it will explain like what kind of objects you should get. So it's predictable, it's equilibrium, it's well-controlled, but at the same time, it's usually very few components in terms of diversity of components. So if I take a micelle, maybe I have 1,000, 10,000 bricks inside my micelle, but they are all the same. So in terms of component diversity, this will be monocomponent, one component. With block, I think there are people working with block copolymer, I think, in the room. With block copolymer, maybe you have one, maybe you have two components, right? Because when you start to think, I will do self-assembly and I will use 10 components, then it starts to be very challenging. And when you go more, so we see with origami, we can do something which is quite amazing, but in general, you deal with very few components. One, two, multiplied by many, but in terms of diversity of components, it's difficult, because otherwise you have too many kinetic traps. And so you have objects that tends to be not so reconfigurable. So because again, if my physical properties of my, for example, surfactants tells me that I have to do a micelle that is 10 nanometer, then I will always get micelles that are 10 nanometer. Okay, it will not, my micelle will not transform into a cube or into a snake or into a dog. No, it will stay a sphere. If you look at living systems, we are out of equilibrium, always. We are out of equilibrium because when we are at equilibrium, we don't want to be at equilibrium because equilibrium means death. So I think most of us want to keep alive, and when we are alive, we are out of equilibrium. So living system works in a way that they are maintained out of equilibrium, because at equilibrium you have no more any reconfigurability. You are in a fixed state. So to have something that is dynamic and alive, what life is doing is consume energy and use this energy to maintain ourselves in a quite stable state. I am quite stable state, right? I have a shape. I have some solidity, so I'm quite stable, but at the same time, the stability is not the equilibrium. It's because I'm consuming energy, right, through food that's converted into ATP, and this ATP is used to make work all molecular motors, all the things, respiration, breathing, all these machines and metabolism we have in our bodies, make us a self-assembled system that is out of equilibrium, that is consuming energy to be maintained. And this is called dissipative. This is called dissipative because it takes energy, so it dissipates energy to be maintained in a given state. This is very, very rare in synthetic systems. There are very few synthetic systems that consume energy to be maintained in a given assembled structure. So living systems, they are out of equilibrium, and we can consider them as quite complex and mysterious. Okay, there are so many things. Even in a butterfly, if you start to go inside the butterfly, you will see something extremely complex. But there are some quite interesting properties. Dissipativeness, they can consume energy to be maintained in such a state, but this makes it possible to be highly dynamic and reconfigurable. That is quite interesting. They are highly multi-component, so many components in a living system, and this is produced by self-assembly. It's not produced by directed assembly. Nobody is coming to assemble my butterfly. It's really self-assembly, right? And they have all these properties that we have talked about adaptability, reconfigurability, and evolutive assembly. So again, we'll see whether with some colloids we can do some colloidal self-assembly, but try to go to all these quite interesting properties that we don't have so much usually in synthetic systems, such as multiple component character, not so much today, but dissipativeness, adaptability, reconfigurability, and collective properties, as you will see. So I will show you, I will have three parts in this lecture. The first part will be on something that is not so well organized, but quite interesting, is the coffering effect. And we'll just show you a bit what, with this coffering effect, we can try to do. Then I will go to something much more organized, colloidal crystallization. And we will see that we can get some interesting properties, such as structural colors, like that. And the last part, I will speak about crystals that are dissipative and that are behavior that are very similar to living systems, even if they are very purely synthetic. So I'll start with the famous coffee-ring effect. The coffee-ring effect is an effect. And for the coffee-ring effect, you need one ingredient, which is, you did some hands-on. So what is the most important components you need to have to get the coffee-ring effect? It's just a training for the evaluation. Don't be stressed. We will evaluate you with questions. So maybe we can practice. So, what is the main ingredient for the coffee-ring effect? Once, if you have to say, I need one single ingredient, and if I have this ingredient, the coffee-ring effect. It's? This is too easy because if you write, okay, what do you think? You need colloidal particles? No. You can do coffee-ring effect, for example, molecule inside the drop. So it works with colloid, but it's not necessary.
Room temperature.
This is the dependence, but I don't need. I mean, you can have coffee at any temperature somehow. Right? It's not the necessary component. What else? Liquid drop? Yeah, we need a drop. It's true. It's true we need a drop. But what I can say, if we argue, I can give you a drop that will not do the coffee-ring effect. And then you lose. And I win. Something that is not evaporating. This is true, you need a non-volatile compound, but again, you can have a drop with non-volatile compounds, and there will be no coffee-ring effect. So something that is really make the coffee-ring effect happens. What?
Three-phase contact line. Three-phase contact line.
You need a contact line, but you always have contact line with a droplet, and I can give you a droplet that doesn't do the coffee-ring effect.
Yes.
Right? No, we can do coffee-ring effect with another interface.
If it's possible to do the rings, copy ring in the like inside the
In vacuum, then it depends what you call vacuum. If I go to space, but then yes, I will not have coffee-ring effect. But I want a component that makes the coffee-ring effect. Pinning. You need contact line pinning. So the drop is not enough. You have many systems where the drop will not do the coffee-ring effect. So it's something, it's not so easy to say, because when you check papers and when you check internet, people will say it's gradient of evaporation, blah, blah, blah. It's we see in coffee, decant, blah, blah, blah. But very important is the pinning of the contact line. So you need a drop that is pinned on a surface, right? So yes, as you said, you need something that is not volatile inside the drop. It's correct, but this is not at the origin of the coffee-ring effect. What is at the origin is the pinning of the contact line. Because before I was looking at drop drying, before I started, I thought I was naive. I thought the drop was just evaporating like that, just becoming smaller and smaller without thinking too much. But in fact, in some real situation, the contact line is pinned, and when the contact line is pinned, then the drop is not evaporating like that, but it's flattening like that. And this is extremely important, because this is the gradient of evaporation at the contact line. At the contact line, you have evaporation that is larger because you are losing more molecular vapor near the contact line. So like in a swimming pool, where you have the aspiration to filter water. Hello. Why it's bugging this? Okay. Where I am here. Okay. So, because the evaporation is stronger on the edge, because you have a loss of solvent that is larger than on the top, this creates a gradient. So it creates a flux of molecule that is larger here than here. So it's like if you are in a swimming pool, when you have this aspiration to filter water, if you are losing your swimming suit will go to this because you have the flow. And here is the same. You have a flow that develops in the drop because you have a loss of molecule on the edge that is stronger than on the top. And this flow will transport everything. And since the contact line is spins, it will accumulate there and it will ring to a ring if your drop is circular, and it will ring to just an isotropic distribution with the shape of the initial drop. And it's called coffee for some reason, but it has nothing to do with coffee. It's actually difficult to do coffee ring effect with coffee, because coffee is full of surfactant and many things. But as soon as you satisfy this condition of having a pinning drop, you will have coffee ring effect. Tears, raindrop, paint, ink, wine, coffee, tea, blood, all these fluids will do a coffee ring effect if they are in such situation. So I will not do a class on all the properties of the coffee ring effect, but there are some key features. The first one is, you see this beautiful stain, right? So the droplets were not so spherical, but things were accumulated at the edge. And if you look at this, and if you track particles, this is with some experiments we did, you can see the radial transport, okay? So indeed, you have a flow inside your particle, and it's transporting the things toward the contact line. And if you follow a single particle, you will see that the speed is quite steady, and at the end, when your drops become very flat, you have a strong acceleration. Suddenly, the drops, everything is going super fast in your droplet. And I think you saw it maybe during your hands-on, is that if you look closely at the ring, you will see that close to the edge you have crystalline organization, because particles in this case are repulsive, so they are packing inside this small space. And it's like if you don't like each other, and if you confine you in small space, you will try to be at the larger distance to each other, and the best way to do that is to make a crystal. So they crystallize. For some reason, you have different packing. Here you have a square arrangement, and then you have hexagonal packing. It's typical in the coffee ring effect. And you see that when you go toward inside the ring, you have a transition between an ordered state and a disordered state. I don't know if you saw this in the hands-on, or did you see this transition between crystalline and amorphous state in the ring? Did you see or not? Yes? No? I don't know. Okay, but in general, you will see that if you have enough particle, and the reason is that you have a flux of particles during the drying, so particles go there. And then when they arrive to the contact line, you have a new particle that arrives, they repel each other, and they will crystallize. But the thing is that you see that the flux is increasing, and so you have a larger and larger amount of particle that is coming. And if you look at the characteristic time, a particle needs to crystallize, and the characteristic time a new particle arrives, there is a transition where the new particles arrive too fast. Okay, so it's like you hate each other, you would like to crystallize, but there are too many people arriving, and then it's jamming. Okay, and then you start to have something totally disordered. So this is typical feature of the coffee effect that you will find everywhere. So if you have just a small number of particles, you will have only a crystalline organization, and if you have more, you have crystalline and then amorphous. And if you put a size, two sizes, I think you saw this also during the hands-on, you will have a segregation in the meniscus, and you will have the smaller particle that are followed by the bigger particle. This is what you saw, right? Yes? So do you validate what I say as an expert of the coffee-ring effect? Am I correct?
Yeah, so they have that some people able to do the mixture of polystyrene with different sizes.
Yes.
So they could able to see that one.
Yes, yes. So everyone agree that these are the characteristics of the coffee-ring effect, right? Yes. Do you agree?
Yes.
Yes?
Yes, that way.
So now I will reply to your problem because you say, no, you tell me you need air, right?
Yeah.
Which I think most of people believed until recently. Because what I show you is not a drop that is evaporating. It's not a drop that is evaporating in air, actually. It's a drop that is in another liquid. In fact, coffee-ring effect is even more universal than people were thinking. So far people were thinking, this is universal. If you have contact line pinning, you have this behavior, it's called a coffee-ring effect, and you have all this property, radial transport, crystallization, segregation of particle, all the property I've showed you. Everything I showed you is not a drop that evaporated air, but it's a drop in another liquid. Okay, so you put a drop, another liquid, and here it's not evaporation, it's just my water will just transfer to the other liquid. So my water will just dissolve in this other liquid little by little, and you see that you get all the properties of the coffee-ring effect. So it shows that the coffee-ring effect is something even more general that we could think about. And I think as a new definition, you have to say that it's even not enough, you don't need evaporation, you just need a transfer of solvents from the droplet to the outer medium. And as soon as you have contact line pinning, and as soon as you have solutes that doesn't dissolve in the outer medium, then you have the coffee-ring effect. Okay, so we see the coffee-ring effect. It's universal, it even occurs inside liquid, so you can have liquid-liquid coffee-ring effect. And then, in fact, you will see many times, if you check on internet, if you check papers, you will see many times that it's a problem in many situations, especially in some application. For example, inkjet printing, DNA chips, where you print when you spot DNA or when you spot proteins. People want to have something uniform, right? In life, we don't like things so uniform because it's boring, but usually for application, for industry doesn't want diversity, they want something uniform. But we can think also when you can do this kind of things with coffee. This is Totoro, you know Totoro, right? No? You don't know Totoro? From the Studio Ghibli in Japan? I recommend to watch Totoro once in your life. It's a very nice animation from Japan. And it's well connected to the spirit of nature, so you can check this amazing animation movie. It's for kids, but it's for everyone. And then you can think also to use it as a tool. Okay, so I would like to show that you can understand a coffee-ring effect, and if you understand, you can use it as a tool. It can be used to do diagnostics, or it can be used also to control how you pattern particles. So coffee-ring effect is complex. There are many parameters that can affect the coffee-ring effect. You saw temperature during your hands-on. It's affected by so many things: surface tension, viscosity, surface, nature of your liquid, so many parameters. But I think there are two main effects, two big categories that can affect the coffeeing. One is the interactions. So changing interactions in your droplet can affect the coffeeing effect. For example, you have particles that attract with each other, so then they will aggregate, they will sediment, and then your coffeeing effect will kind of disappear. And you have flows. You have flows because you see this is based on flow inside your droplet. So anything that will perturb this flow will perturb the coffeeing effect. The viscosity, for instance, surface tension is a mahogany flow. Flows can really perturb this. So then if we want to have a control of this coffeeing effect, rather for diagnostics or for patterning or whatsoever, you need, I think, a way is to either target flows, either target interactions. And what I want to show that, again, interfaces are probably the best way to control this process, because interfaces, many things happen. So I would like to show you that by controlling interactions at interfaces or flows at interfaces, then you can have really quite interesting control of the coffeeing effect. So we made this discovery some 10 years ago now. That we'll start by considering interactions at interfaces. And the idea was to say that somehow, when you have a droplet, you usually think a lot about the solid surface, because this is where particles will be deposited. So many people have worked on solid surface. Many times we think about what to do inside the drop, but that, in fact, something that for some reason has been neglected for many years is that you have the surface of the drop. So many people forget that here you have an interesting playground because you have an interface and many things can happen, and maybe we can use this interface. So it is this very simple experiment where you just take particles and a surfactant of opposite charge, something extremely simple in terms of experiment. And we are working below the CMC, below the critical missile concentration, because here we really want to deal with interactions. We don't want to generate strong manganese and so on. So we put some small amount of surfactant, nothing large. And we found this, like when you increase surfactant concentration, you have the coffeeing effect. And if you are at large concentration, below CMC, you have the coffeeing effect. And if you are in between, there is a very small range of concentration where you will have absorption of your oppositely charged surfactants. And in this regime, when it makes a monolayer, particle will adsorb at the liquid-air interface, and they will accumulate at the interface instead of being transported, and then you have a uniform deposit. And when you go at too high concentration, your surfactants self-assemble and will tend to make some multi-layer, so your particles will become cationic. So if you look at electrostatics behavior, you start, for example, for negatively charged zeta potential, coffeeing effect, you neutralize your particle, you have a disk, and then you overcharge a particle, you have a ring. And this works for any system. If you change to cationic particles and take anionic surfactant, you will always have the ring, disk, ring, and you can change the particle nature, you can change surfactant nature, you will always have this behavior. So it's quite universal behavior. And this is what makes it interesting, and I will draw you what you need to remember. You need to remember that, yes, and this is kind of right. Yes, thank you. So you'll be like here. So this is my concentration. So my particle, I draw negatively charged, but can be cationic, okay? So here, I am making a monolayer, and I neutralize the particle. Here my zeta potential is strongly negative, here my zeta potential becomes almost zero, and here my zeta potential becomes overcharged. And this works also for the opposite charge system, so cationic particle and anionic surfactant. So here, when I have the situation, this is my pattern. I have a ring. I have a disk. And I have a ring. Okay. So now, let's see what we can do with that. So I will show you two patterns. Okay, this is the example I explained to you. I will not. You have understood, I guess. And then let's look at here. We'll compare this and this. I will show you two droplets in this situation, this situation. So here, I will have the usual coffering effect, and here I just put this concentration around a particle will assemble at the interface. So you will see that on the left, you will see the flow that developed, the coffering effect that is forming. All right, so you have the coffering effect, I'm a deposit, and on the right, my particles accumulate at the air interface, so they don't move so much. And then I have uniform disk, right? Okay. Who has some eye problems like me? Who doesn't see very well? Can you remove your glasses? Okay. So without glasses, right? Can you see the difference?
Yeah, a little bit.
Yes, you see it's different. Even without glasses. With your glasses, you see the difference, right? So you see that these two patterns, we see they are very different. And it's very interesting because inside, it's just a difference of interactions. So what you see with eyes, that's nice. I like this animation. When you see, what you see with your eyes is the interaction between a surfactant and a particle. So even without any microscope, even if you remove your glasses, you can see an interaction, a molecular interaction, just at looking at the pattern. So this, I would like to tell you that this could be used, a pattern, as an image of interactions, and this I call it a diagnostic. Because now you can use this maybe to measure pH, maybe to measure redox potential. Maybe you can use it to detect a disease. So this is what we did many years ago. And our target was this disease, sickle cell disease, SCD. It's a genetic disease. It's due to a mutation. It's the most frequent genetic disease in the world. The most frequent genetic disease in the world. And in fact, it happens everywhere you have malaria. You have this pressure, environmental pressure when you have malaria, to make this mutation, because if you have this mutation, you are better protected against malaria. But you are protected as long as you are heterozygote. It means that you have only one mutation in one of your chromosomes. The problem is that if you have one mutation in each of your chromosomes, so the one coming from your father and the one coming from your mother, then you have the sickle cell disease. And this is a very terrible disease, very painful, with a strong mortality among children, where you have it's multifactor. You don't die from the sickle cell disease, but you die from the consequences: brain seizure, heart seizure, all kind of things that happens because it affects the blood hydrodynamic properties. So as soon as the blood is circulating improperly, it's painful and it can be deathful. In some country in the world, because of multifactor, but 90% of children with SCD will die before 5. So it's quite serious. And there are countries, for example, where you have, for example, Cameroon, you have more than 40% of people who are heterozygotes. It means that they have a 1/4 risk to get a child with this disease. So it means that you need to have tests, and you have two challenges. You need to test newborns, so babies, as soon as possible to know if they have the disease, right? So that you can start to prevent, and if you, as early you know, as more you can bring solutions and to accompany the child and the adult, hopefully. And also, you need to screen adults, not the people who are sick, because doctors can recognize the symptoms, but more to detect who are heterozygotes, so who is carrying this gene that could be transmitted to the child. So the idea is that if parents are informed, then they know there is a risk, and then they can test as their child, and they can take their decision, but at least they know. The problem is that most of testing solutions are distributed by diagnostic company, and they make profit of it. And these diagnostics are very expensive. The cheapest one are kits, you know, like for COVID tests or whatever. But this is already a few dollars. At a few dollars, you cannot make systematic screening at the scale of a country. If you consider some countries, they cannot afford systematic diagnostic if one test is a few dollars. So you need to find solutions to make something that could be very cheap. And also, if possible, something that you don't rely on a company, so that you can really develop the things without relying on the company. So this is what we've done with the coffering. So here is just pure hemoglobin. So it's hemoglobin from patient. So the blood was taken from patient. We take the hemoglobin protein, and then we mix with particle. So if you have no particle, you have a coffering of the hemoglobin. And now if you put particles with very many conditions, but you have some conditions where everything is fixed, concentration and so on. And if the patient is healthy, you have the coffering effect. And if the patient has a disease, you have a disc. And why you have a disc? Because you have this mutation, you change one amino acid from hydrophilic to hydrophobic, and then my hemoglobin just behaves as a surfactant. So actually, what happens is you go to a situation a bit like that, you have a ring, and when your hemoglobin, you add this hydrophobic residue due to the mutation, the hemoglobin will become like a surfactant, and we add some on the particle, and on the particle we add some at the liquid air interface, and then you have a disc. And what is quite interesting is that, is that you can see with your eyes a change at a molecular level. And you don't have fluorescence. You don't have antibody. You don't have any machines here. You just see by eye molecular change at a protein level. And this is well suited for this disease because we have a lot of hemoglobin in our blood. Our blood is mainly protein. Our blood is mainly hemoglobin. So I will not generalize this to other diseases of protein, but for this specific disease, it's very interesting. So you have the possibility to see protein-particle interactions directly with your eye, And this can give a concept to make a very simple, very low cost, very distributable diagnostics for very important diseases. So this was done in 2016, published in 2016. It was purely fundamental work, where we work with purified hemoglobin and so on and so forth. We also check different proteins because we try to give some general behavior, general knowledge. And then with that, we say, okay, maybe we can try to bring this to the reality. So then for doing that, you need to ask fundings and so on, and it was very difficult. So it took a lot of time so that we could have support to bring this to the real world, to the reality. But a few years ago, we could finally get some funding after many efforts, after many years of effort. We got funding, and we have a collaboration with a group of really great doctors who are specialists of this disease and who have worked in Africa. And we decided to go to reality, so we take directly blood and we make stains, we just make drop, and we take patterns, and we take a bit of artificial intelligence, smartphone, so drop, smartphone, and we have a diagnostic. And we have done a first test in Democratic Republic of Congo in Africa, in real situations, so in a real, directly in the city, with very, very simple, just put drops on glasses. And we had 100% sensitivity of our test. So now we have ongoing clinical tests, large-scale clinical tests, and we hope this will be validated so that people can use it. And we do it without doing any company. So it's our idea is to be non-profit. So our idea is to train people, train doctors, so that they can do without relying on external companies. So sometimes, such matter can bring you to some interesting impact in the real world. So, but we can also do some fun with the coffee-ring effect, and we can use it also to organize particles, to control the particle patterning. So let's remember this slide. It's summarized here, and then you see that we have surfactants that are at the origin of this interaction. So then if you take surfactants that you can modulate their properties, then you will be able maybe to modulate this effect. So we started, for example, with a redox-sensitive surfactant. So it's a ferrocene surfactant. So you have the head, you have the tail, and when you oxidize this molecule, it becomes more charged, so less hydrophobic, if you want. And if you charge the molecule, it becomes less charged, so more amphiphilic, more hydrophobic. Okay? So before asking you a question, if you understood, you see that here my surfactant is doing this. So if I take a more hydrophobic surfactant, this assembly will be easier. Okay, so this frontier will be lower. So this is surfactant 1. And now if I take surfactant 2, which is more hydrophobic than this surfactant 1, then if it's more hydrophobic, this assembly, like a micelle, will occur at lower concentration. So it means that this neutralization reaction will be at an earlier stage compared to this guy. Sorry. So it means that here my ring will be here, and my disk will be here. And my ring will be here. Okay? So if I increase hydrophobicity, I will switch the frontier to the left, and if it's more hydrophilic, I will switch to the right. So now I have this redox molecule, okay? It's in your brain? So what do you expect when I will, for example, take my particle suspension, and if, for example, I do oxidation reaction? Will I go for ring to disk or disk to ring? What happens when I do the oxidation of my surfactant? So when I go from the oxidation is when I take out an electron, so when I go from left to right. For example, because I have oxygen or because of water, I have oxidation. So do you think what will happen when I do this from left to right? Yes?
I think the CMC concentration
Yes.
will shift
Yes.
over either oxidation or reduction.
Yes. So when you oxidize, you see you go from left to right. The molecule becomes more charged and less hydrophobic.
So the CMC would shift.
So CMC should shift left exactly because should shift to the right because it's less amphiphilic. You see, it's less hydrophobic. So when I oxidize, my molecule becomes less amphiphilic, less hydrophobic, so my CMC will be larger. I need more molecule. So I should go to that direction. But it's also more charged. So it means that it will be more efficient to neutralize the particle. So now we are in a situation where, in terms of amphiphilicity, this should favor this direction. But if we consider the electrostatics, then my surfactant will be more efficient to neutralize because it will have more charge. So more neutralization means it will be easier to reach this state. So going to this. So amphiphilicity should shift to the right and chance should shift to the left, so we don't know. And it happens that this is a charge effect that wins. So when you oxidize, your surfactant is more charged, you neutralize the particle, and then you reach the disk. And if you do the reduction, you have the opposite behavior. And you have the ring, and you have the disk. And this shows that, again, you can modulate this pattern. And here is a redox reaction. Redox reaction is quite interesting because most biological reactions are redox. So you can use this, for example, to detect sale of a state or something like that. And it shows also that in this case, it's dominated by the electrostatics rather than by the hydrophobic interactions. Light. We like light actuation. We have done many things with light. And then we can just use photosensitive surfactant, as I showed yesterday. So we developed this molecule that we use a lot. It's a surfactant that you can shift between two states. So same principle. If I apply UV, my molecule becomes polar, so less hydrophilic, less amphiphilic, less hydrophobic. So my CMC will increase. So I will go to the right. And if I apply blue light, it's the opposite. I will have a surfactant that is more hydrophobic. So I will shift my frontier to the left. And this is indeed what we have, actually. So you see that when we have without UV, my surfactant is more hydrophobic, so I will assemble more easily to the particle, so I neutralize at lower concentration. So I will go to particles that are charged, neutralize, and overcharged. And if I do with plus UV, since my molecule is less amphiphilic, this self-assembly will occur at higher concentration. So I'll have charged particle, neutralize, and overcharge. And I have a shift, okay? And if I look at the pattern, I have a ring, I have a disk, I have ring and ring, like here. And here, if I apply UV, I have a ring, and a disk and a ring. So I really respect this, this general behavior of assembly. And with this, you can, for example, fix a concentration. And then with light, I can shift between these two patterns. So I can start with a ring, and when I apply UV, my particle will start to become sticky to the surface and will do a disk. So this is just an example. You take many droplets, they are all the same, and we just put UV on that droplets, and you will see that these droplets, I don't know if you can see, it's a bit dark, but you will see that these droplets will form some disk, and one that were not illuminated for some rings. Okay, so you can really control how the pattern is occurring with light. So this, if you can do with mean droplets, you can do this kind of patterning. And by adjusting the amount of light, you can go from very marked ring to a uniform disk, and you can make some transition in between. But this is at the level of the drop. So it's like I decide if my drop is a ring or I decide if my drop is a disk. So can we do some patterning inside the drop? Yes, we can, because Subramanian exists. He came to the lab many years ago, and we wanted to use light, in this case, not to use interactions. This is what we did before at low surfactant, but mahogany flows, you know, because coffee ring effect is about interactions and flows. So to go toward flows, we decided to go to high surfactant concentration, and then we just generate mahogany flow. And when you generate mahogany flow on the surface, you can develop some bulk flow, and we will use this to trap particles inside the droplets. There is a bit complex pattern going inside, but you can create a bulk part where your particle will be trapped, and they will be deposited where you want. So where you put the light, the particle will be assembled. And what is interesting in this system is that it doesn't depend on your droplet because it's controlled by the flow. So you can do all these kind of patterns, spots that you can move, or patterns. For some reason, I asked him to do this kind of patterns, and 10 years later, I figured out that somehow there was kind of hidden message in these patterns, because we can somehow have something that looks like calicut. So what is nice is that it's a flow-based method, so you can transport any particles you want. And at that time in the lab, we used to have a lot of fun with coffee. So we say, if it can work with any solution, we should do it with coffee. So we take commercially available coffee. You don't know at all what is in commercially available coffee. We didn't have Tata coffee. We just have Nescafe. It's from Switzerland. It's bad, but it's like that. So you just powder, you put water, and you have something called coffee. You really don't know what is inside. Really don't know what is inside, and nobody will tell you. Nobody will tell you, and this guy will never tell you what they put inside. So we just take this drop. We don't do anything. just put our surfactant, and you see that we can pattern somehow inside this drop this Calicut letter, right? So we just make a C pattern, and we can pattern this coffee even in this totally unknown solution. So it shows that it's very interesting to use flows, like even in a unknown solution, you can do something. So covering effect is, if you have to remember something, covering effect is about interactions and flows. And interactions and flows can be used to control the deposit morphology, and you can use it for patterning. But I also show that because you have this effect, you can do the other way around. You can look at a pattern to understand what happens inside your drop. And if you talk about interactions, then you can know what happens inside your drop, and you can make a diagnostics. And in terms of interactions and flows, I try to show that it's quite interesting to target interfaces again. So interfaces are really cool. Again, everything we did was at interfaces, and we can have a lot of cool and interesting behavior with light, with diagnostics, with redox, and so on and so forth. So now, if I look back at my coffering effect, okay, it's uniform. But you saw when you check this by electron microscopy, it's not organized. You have an amorphous assembly here. So here it's crystalline, but it's not very, it's just a very thin disk. So, and to be really crystalline, you just need to work with small amount of particles. So I wanted to know whether it could be possible to have something that is organized, that crystallized, that self-assembled in an organized way. And again, I wanted to do this at this water surface. So we could do that with a very, very simple method. This method is, I will not do it with this glass because it will be dangerous, but basically, I have empty glass here. So you put, you take a smaller container, of course, because you need capillarity, but you put a particle suspension in a container, and you flip your container. So your particle will finish by reaching the interface. You cannot work with 10 nanometer particle, but if you work with micrometer or hundreds micrometer particle, they will reach the interface. And then you flip again. This is the experiment. Very, very easy. And then you just look at the microscope at the surface. Okay? And then, if I don't put any surfactant, my interfaces is free of particle. If I put my magic concentration, if I put this concentration here, I have an assembly that is amorphous. So my particles adsorb at the interface, but they are not organized. But no, if you add very, very small amount of surfactant, micromolar concentration. So now I'm talking about 10,000 times smaller or 1,000 times smaller than the CMC. Very tiny amount of cationic surfactant. This is what you get. What you get here is particles that self-assemble and that crystallize under your eyes. These are monocrystalline domain, and these are the grain boundaries. So what happens here is that this amount of surfactant is enough to have adsorption of the particle. It's because particles are charged. The liquid surface interface with air is also charged. So you need to screen this barrier, electrostatic barrier, and just a small amount of cationic surfactant is enough to screen this barrier. But, so my particles, they adsorb, but in contrast with this situation, my particles remain charged, okay? So what will happen is that they are adsorbed at my interface, and if I take one single particle, the single particle cannot deform the interface. It's too small. But if you have many of them, the collective weight of these particles can become enough to deform collectively the interface. Okay, it's like if I hung to the ceiling, maybe nothing happened, but if we all hung to the ceiling, maybe everything will collapse. So here the particles, if they are in large numbers, they can deform the interface together. And when they deform the interface, they will come closer. So if they come closer, their density increases. So it means they will deform more. So you have a positive feedback. So it's a self-amplifying mechanism. So that's why it's called collective thinking. So collectively, the particles can deform the interface and accumulate at the center. So it's really self-assembly. It's particles that self-confine. You know, people, when they do colloidal crystal, usually they put particles and they press with physical barrier. But here, it's self-confinement. The particles, they attach and they self-confine. But they are charged. So if they are charged, they repel each other. So they self-confine, so you have long-range attraction, and short-range, you have short-range repulsion. And when you have that, you have crystallization. Okay, you bring many things together, but they repel, so they organize, and they crystallize. So I think it's quite beautiful of a self-assembly that can lead to something very organized. And if you look with just white light, you will have structural colors, and each domain gives one color because it has different orientation. And this is quite nice. Then you can play with the system. You can tune the interaction just by surfactant. If I increase surfactant concentration, my particle will become less and less repulsive, and then my crystal will start to be less and less ordered. So I'm losing, you see, you have very, very nice organization when I'm very repulsive, and I'm progressively losing the repulsion. And then with that, I can control the grain size from very small grain to very large grain. And this is a very universal method. It works with any particle. So it can be polycarbonate, silica, gold, silver, whatever you can imagine. We did with spheres, with cubes, and size between 100 nanometer and 10 micrometer. Anything will crystallize with this system. So it's a very universal method. Just need this the key point is this very micromolar amount of surfactant. This makes all the difference. So it's nice to have crystals, but liquid interface is interesting, but it's not very convenient to manipulate. So we wanted to transfer this to this crystal to an interface. And at the beginning, we try, to transfer this a bit like what you did with these liquid marbles and so on. And it's very difficult to transfer because you have all kinds of stress that occurs when you want to transfer. So it's possible to transfer, but for example, here, look, here it was transferred, but you see I generate many defects when I transfer my substrate. So it's not very, very interesting. So we say, okay, let's do it a little bit in a smarter way, and we did even more simple experiment. We take a droplet, we flip it, and we let it dry. That's it. Okay, this is the experiment. We just take the droplet, flip, and let it dry. So what happens here is that my particle sediments, when they are in this hanging drop configuration, and if I have this very tiny amount of surfactant, they will adsorb. So they will crystallize, and because they are adsorbed, they will remain monolayered. Otherwise, they will make some multi-layer because they push to each other. And then they will crystallize, and my droplets will bring the crystals directly on the surface. So if I play again the movie, so here is the side view. So my drop is just drying in this hanging configuration. And here, this is a top view. And you will see at some point some colors. So these are the structural colors. So what you will see, this is just silica particles. They have no color by itself. But you see they start to organize and make this very beautiful color pattern. Here we are here. My crystal is on the top of the droplet. My droplet is drying, and it will, by itself, deposit the crystal on the surface. So it's purely self-assembly. There is nothing to do. So you have a little bit of extra particle in the middle, but all of this is monolayered and nicely crystalline. And then you can play with all different parameters. You can even do monocrystals. And you can start to have some funny assembly. For example, you can make a first crystal, then you can put another drop on it. So you have a second crystal that crystallizes with the same interparticle distance, but then when they will come together, they will have independent orientation. So you have the same interparticle distance but independent orientation, and this gives you this very nice moire patterns, for example, typical of optics. And then you can also play with different particle size, and you can do size sorting with very interesting patterns with the small particles. You see you have a ring of large particles, then small particles, and large particles, and everything crystallized. And you have this interesting behavior. And just to finish with that, you can make a double flipping. So you flip, you let the drop crystallize, and when the crystal crystallizes before the drop is drying, you flip it back, and then the crystal will be transported to the edge. And then you will end up with a ring of crystal, like that. So you have now a crystalline assembly that has this shape with nothing in the middle. So we call it iris, like what we have in the eye, and we have this beautiful colored pattern. Okay, so you see that we started from coffee where it's very large-scale patterning. We don't have any interaction in any local organization. And then this was mainly controlled by surfactants at moderately high concentration below CMC, but let's say CMC over 10. And then if you go to CMC over 1,000, over 10,000, you can start to have some very interesting self-assembly behavior where you can crystallize the particles. And then I will finish to show how we can have a bit more dynamic and reconfigurable assembly of this particle. So everything will be at the liquid air interface, like what I've showed you. So we'll keep this system. So we prepare this colloidal crystal at the liquid interface with this very simple method. And then to have dynamics and reconfigurability, for instance, using light, but just use photosensitive surfactants. So we just do the same experiment with photosensitive surfactant, and this is what we have. So in this case, we start from the disordered state. So these are the colloids. And when you will see the change of color, it means that I apply UV. And when it comes back to this reddish color, it means that I remove the UV. So you see that when you apply UV, in just a few seconds, the system crystallizes. And I remove UV, the systems go back to the disordered state. Okay, so it's continuous. You see the timestamp, so it's not a loop. So I remove UV, the system goes to disordered state. I put UV, it crystallizes in a few seconds. Right. So you can see crystallization by eyes in a real time. This is what is cool with colloids. So you can see atomic process at micro scale. So you can switch. Well, it's always nice when you do photo control. But what I think is very interesting in the system is that, in fact, this crystalline state is consuming energy. So it's a crystal that needs energy to exist. As soon as you remove its food, it goes back to the disordered state. So in fact, you have a dissipative assembly. You have a dissipative crystal like living systems. The system is consuming light energy, photochemical energy, to be maintained in its ordered state. And this is due to some quite a bit complex dynamic out of equilibrium behavior. But basically, you have the surfactant. They have this continuous adsorption-desorption. And when I will apply UV, I will desorb the surfactant. So then my particle will be repulsive, so they will crystallize. As soon as I remove light, my surfactants adsorb, and then I repopulate my situation. So this is my equilibrium state, where my crystal is in an amorphous state. And as soon as I put light, I pump out the surfactant, my system crystallizes, and if I remove, my surfactant reabsorb, and I go to the disordered state. So what is cool is that you have a photosynthetic state. This is kind of the equilibrium, and here, when I bring the energy, my system is organizing. So it's typical example of dissipative assembly, and this is exactly how living systems are working. So we can do something maybe a bit more familiar with what we have shown during this week. Now we can take an ordinary surfactant and use light-absorbing particles. So we start from this. You will see the particles were not so nice compared to the other, not so monodispersed, so we have defects. But these particles, they are absorbing light. It's not gold, it's not photonic, but it's just some polystyrene and they have some magnetic inclusion inside. We don't put a magnet here, but it's just they absorb light. So when you put light, temperature increases. So you see, my system here starts from a crystal. When I put light, my crystal expands, and when I remove light, my particles go back to the crystalline state. At the beginning, we thought like, okay, it's just melting the crystal. It's just we increase the temperature of the crystal, so my particles have more Brownian motion, so then they do this. But in fact, this is due to Marangoni flow again. In fact, it's because when I shine light, temperature increase just at the level of particle. So now I have a Marangoni stress like that. So it's expand the particle, and then my particle then with Brownian motion will go to the melting state. So it's first expansion and then diffusion that is through Brownian motion that go to the melted state. And as soon as I remove light, my system crystallizes by this collective sinking mechanism. So here we have something that is very different from the previous case. This is very equilibrium configuration, and we are just using this flow to expand, disorder the crystal, and it will crystallize again as soon as we remove light. And you can follow, analyze all the particles and study all the parameters, all these kind of things. You can check all this in the papers, of course. And then you can start to have some fun. So I will show you. So this is a crystal. It's the same example as just the image before, but it's a bit small. And we put the light here. Okay, so if we put the light here, this is what happens. You have this beautiful effect. So first, let's see. So my crystal is self-assembled, so it's slightly curving the interface. Light is here, so you have thermal Marangoni expansion. Here, I have other particles, so most of my particles will go this way. And then, because my crystal is curving the interface, the particles are going back in the crystal. This is what happens, okay? So I put light, I have Marangoni flow, particles are expelled, and they come back to the crystal. And now, if you look carefully, but it's difficult to see from your side, from your distance, I guess you see the hexagonal organization from where you are or not? You see it's organized, right? Yes? No? Well, if you are close enough, you can see that you have a very nice hexagonal pattern. If you do the Fourier transform, you will see very nice peaks. I have very nice crystallization. So I have a crystal. But what is very interesting, if I track a single particle, the single particle is moving. So I have a crystal, I have a steady state crystal by positional order, but I have a flux of particles inside. So this is called, this type of organization, which is quite unusual, it's called a living crystal, in the sense that you have positional order, but you have a flow of particles. If you take a usual crystal, like a piece of salt, you have a crystal, everything is well positioned, but nobody is moving. You have no flux of matter. Here you have a crystal, but you have a flux of matter. Matter is entering, matter is going out, but everything remains perfectly crystallized. And this is what I see in the first example of a not only living crystal, but self-feeding. So the food that is repelled is also coming back to the crystal. So you have another steady state level of the system, because what is expelling is also coming back to the crystal. So I think I show you several examples of what we can do with self-assembly of colloids in different perspectives. Coffering effect. I try to show you that how interactions on flow can control this behavior, how it can be used for diagnostics, how you can use. What is interesting is not what we have done, but is this idea that if you look at a pattern, you can give or understand what happens inside your liquid. So this is what I call diagnostic in general. And then you can, if you understand a bit, you can do a bit of patterning. And then you have this colloidal crystallization and liquid interface, which compared to the regular methods where people compress and so on, this is purely self-assembly. In this case, it's the particle itself that go to the interface and confine and crystallize. And this is what is super interesting in this process, is you don't have to do anything. It's really purely self-organization. And you see that you can devise very simple drop, like this hanging drop technique, where the only thing you have to do is that. And you do that, and you get at the end a very nice crystal on your surface. And this crystal is beautiful because it has structural colors. So this is, I think, quite interesting interface. And because you're at interface, you can generate also some dynamic and reconfigurability behavior. So with that, I would like to thank all my folks from the lab, and hope you can visit us one day. And thank you very much for the attention for this last lecture.
Thank you very much for taking us through the fascinating world of operates. So, shall we take?
If you want, you can have one or two questions, yes, or you can have a rest also as you want. But I have yeah, few minutes if there is question. Yes.
In the beginning, you were explaining that assembly of synthetic systems.
Yes.
Limited by kinetic charge.
Yes.
While you were doing kind of experiment, how will you find out, like, the values right now? It is not global minima.
Yeah, so it's a very good point. So in fact, in this colloidal assembly, we don't have so much problem of kinetic trap, in the sense that it's monocomponent. And as soon as your crystallization is slow enough, you will have not much defect. But we have defect. As you saw, we have polycrystals. That's a bit a limitation of self-assembly, is that you will see maybe in literature some people making very large monocrystals, but it's very rare to be by self-assembly. Here, our system imposes its kinetics, and if it's going a bit too fast, then you will generate some defects. So here, I think it's not, I don't know if we can say, but see, it's kind of kinetic trap in the sense that as soon as all the particles are coming together, then at some point they will not be able to reorganize anymore. So their thermal energy cannot compete with the compression force, and then here the system is a kinetic trap, because my minimum should be a monocrystal, right? But I have a polycrystal, which can be interesting for some applications, but here we deal with it. So in this case, we still have some kinetical trapping, which is the situation where all my particles are too close, and then they cannot reconfigure enough. So they can reorganize to make these crystals, but at some point when they are constrained. So this you can play, if you decrease the number of particles, we can reach this situation to have monocrystal, but if you don't do anything special, you will have polycrystals, and these are our kinetic traps in this case. Very good point.
Equal to nearly zero.
Yeah.
What happens to the particle stability?
So it's also quite a good point. Usually here, if you work at the scale of the drop evaporation, so they will start to aggregate a bit in the bulk, but usually at the scale of the evaporation time, the aggregates will not be so large to sediment faster than. So what happens that your interface. So you have two things to consider. First is the transport of the particle to the interface. So you have some active transport by the evaporation, so some particles are made, and you also find that the interface is going down. So interface will come in contact with particle. So particles, either they're individual and they will stick to the interface, either they are already in the form of small aggregates and they will stick to the interface. Usually what we saw is that we see some small, like, I don't know, 3, 4, 5 particles. We don't see like massive aggregates. I think the interface is fishing this starting aggregate before they become too big. So we don't have much problem of sedimentation. Maybe for higher concentration of particles, it could be maybe for situation, but we do have, but it's not making precipitation too much. It's really accumulating at the interface. And also probably because this absorption at the interface, we don't need to have exactly 0 zeta potential. So maybe we are sometimes a bit below, a bit above. So maybe the particles are not really aggregated so much, but they will become sticky for the interface.
I was trying something like this.
Yes.
Theta going from
Yes.
positive to negative.
Yes.
And I reached that nearly 0.
Maybe you were very precise and too precise, and maybe at exactly 0 everything is precipitating. Maybe. In our case, we see really this range of concentration where particles were really sticking to the interface. But maybe you are very careful, and at 0, 0, you precipitate. Yes, it's possible. Maybe if they are big particles also, or it could be possible. Yes.
Thank you very much.
You can take the last question.
When we are talking about this
living crystal.
Yes.
So there are two regimes you are talking about, like when you are shining the light, the thermal temperature
Yes.
is increasing and that's why they are moving. And second is the Marangoni
Yes,
expansion.
exactly.
So generally Marangoni is very large force, so it gives
Yes.
great amplitude of velocity.
Yes.
So how you come to know when the regime of thermal energy is just converted to Marangoni? Like how you differentiate it, or you put that concept of Marangoni expansion to that? Is there some value of velocity where you can say the velocity is much more this is accomplished with the Marangoni in that case?
Yeah, the thing is that here, the Marangoni stress is competing with the packing force. So this you have to see that all particles, they push to each other. So you have a quite strong compression force toward the center of the crystal. And in fact, if you compute a bit, the thermal energy you gain by increasing the system is really, really nothing. So you really need a strong stress. And Marangoni stress actually is just here, because you have to understand particles, they repel to each other. Okay, so there is no molecular like cohesion. There is no molecular particles. They repel each other. Okay, they are just here because of their own small waves. Okay, they are the particle. The Marangoni flow is here to really just spread the particle. And so you see that at the beginning they spread, and then when they are far enough, they cannot push anymore on the interface. So at the beginning, the interface is very curved, very compact. Then the Marangoni expand everyone, and then these particles, they cannot crystallize because they cannot confine anymore, and then they have Brownian motion. So you really see this two-step behavior, that is very hydrodynamic effect at the beginning, and after it's really melting by diffusion. I have to go. I have a lecture, a talk at 12. But we see you I see you this afternoon for the best. You.